Welcome to the solutions to the college physics springs and simple harmonic motion problem set. Problems numbers 15 through 17. Let's jump right in with 15. We have a 0.4 kilogram object connected to a light spring with a spring constant of 19.6 newtons per meter. Oscillates on a frictionless horizontal surface. If the spring is compressed 4 centimeters and released from rest, determine A, the maximum speed of the object, B, the speed of the object when the spring is compressed 1.5 centimeters, C, the speed of the object when the spring is stretched 1.5 centimeters, and D, for what value of x does the speed equal 1/2 the maximum speed. Well, being frictionless, all these solutions are going to be conservation of energy solutions, and we start with A, the maximum speed. Well, from our knowledge and lesson in simple harmonic motion, we know the maximum speed is going to take place at the equilibrium position. So we start with our conservation of energy statement. In our initial state, all the mechanical energy will be elastic potential because you have a spring compressed 4 centimeters and the object is released from rest. There's no heights in this problem, so no gravitational potential energy to take into consideration. In the final state, for A, that's going to be at the equilibrium position, where our object is moving at maximum speed, so that's kinetic energy. And at equilibrium, the spring is not stretched or compressed, so no elastic potential. So we go ahead and set that up. 1/2 kxo squared equals 1/2 mv squared. And the halves cancel. We go ahead and substitute. Solve for v algebraically. Take a moment to do so if you need to. And v equals 0.28 meters per second. B, they want the speed of the object when the spring is compressed 1.5 centimeters. So we're going to keep the same initial state at the beginning of the problem, but our final state will now have our object moving and also have the spring partially compressed at 1.5 centimeters. So we have both kinetic and elastic potential in the final state. Again, we start with our conservation of energy statement. And we have our initial 1/2 kxo squared equals 1/2 kx squared plus 1/2 mv squared. Still a half in every term, so we can go ahead and cancel that. Substitute. We have our spring constant 19.6 newtons per meter times our compression, initial compression 0.04 squared equals 19.6 newtons per meter times our final compression 0.015 meters squared, and our mass 0.40 times v squared. Solve algebraically for v, and we get 0.26 meters per second. C wants to know the speed of the object when this spring is stretched 1.5 centimeters. Well, for this we don't even need to do a calculation because its speed at a compression of 1.5 is going to be the same as its speed at a stretch of 1.5 from equilibrium. X values are always measured from equilibrium, so since they both have the same x value, C will be the same answer as B, 0.26 meters per second. D, for what value of x does the speed equal 1/2 the maximum speed? Or maximum speed was calculated here in part A, so half that would be 0.14 meters per second. So again, starting off with our conservation of energy statement, we're going to use the same initial state, and in our final state, this time we're looking for the value of x, for which we now know the value of v. We go ahead and again substitute, same substitutions initially here, and we have 19.6 times x squared plus 0.4 times 0.14 meters per second, and we have to remember to square that as well. You should get, when you solve algebraically for x, 0.035 meters. All right, that'll do it for 15. Let's move on to 16. At an outdoor market, a bunch of bananas is set into oscillatory motion with an amplitude of 20 centimeters on a spring with a force constant of 16 newtons per meter. It is observed the maximum speed of the bunch of bananas is 40 centimeters per second. What is the weight of bananas? All right, I want to start with a diagram here I'm going to show on the left side. And I've used that same diagram we used in a simple harmonic, and the red mass here is the bananas hanging from the spring scale in this particular problem. I placed the spring scale here at the 40 centimeter mark, which will be the equilibrium position for the oscillation. And we're told that the amplitude is 20 centimeters, so 0.2 meters. That means the peak of the oscillation will be up here at the 20 centimeter mark, and the bottom of the oscillation will be down here at the 60 centimeter mark. I'm showing the mass at the equilibrium position. I'm going to use the equilibrium position to be the initial state for mechanical energy, and we know that the speed there is 0.40 meters per second, and that the spring is not stretched or compressed beyond equilibrium from that spot. I'm going to use the bottom spot here as the final spot for conservation mechanical energy, where the mass of banana stops and the spring stretches to 0.20 meters. So again, we start with our conservation of energy statement. Our kinetic at the equilibrium position becomes all elastic potential at the bottom of the oscillation. The halves cancel. We go ahead and substitute. We solve for the mass in this problem to be 4 kilograms. And then to get the weight of the bananas, we simply do a quick little W equals mg calculation, and we get 39.2 newtons, which if you divide by 4.448 newtons per pound, gives us about 9 pounds, just so we relatively know how much that is. Makes sense. Okay? If you have any questions on this problem, make sure you ask in class. Lastly, number 17, we have a pendulum clock that works perfectly on the Earth is taken to the moon. Assumed free fall acceleration on the moon is 1.63 meters per second squared. A, does it run fast or slow there? Justify our answer. And B, the clock started at midnight on the moon. What will it read after 1 Earth day, which is, of course, 24 hours? Okay, so let's start with A here. We start with the period formula for the period of a pendulum. T equals 2 pi square root L over G. And clearly the acceleration on the moon at 1.63 is less than the acceleration on Earth, which is 9.81. So we have a decrease in the acceleration due to gravity when we take our pendulum clock to the moon. Well, an inverse relationship between little g and t, and so if the acceleration due to gravity decreases, our period of our pendulum will increase, and that means a longer period on the moon. Therefore, the clock on the moon will run slower. Okay? Now they ask us to practically apply this to figure out what time the clock on the moon will read after 1 Earth day of 24 hours. The first thing we need to do here is find the ratio of pendulum time. So the ratio of the periods. We're going to take and find and compare the period of a pendulum on the Earth to the period of the pendulum on the moon. The period of the pendulum on the Earth would be 2 pi square root L over 9.81. Period of pendulum on the moon would be 2 pi square root, same length, so that doesn't change, over 1.63. The 2 pi's cancel, the L's cancel, and our ratio simply becomes the square root of the inverse of 9.81 over the inverse, square root of the inverse of 1.63. When we do that, we get TE is to TM equals 0.408. This should make sense to us because that means that time, the pendulum time, slows down on the moon. We understand that actual time doesn't, but pendulum time on the moon, on this pendulum clock, would slow down since gravity does not restore the pendulum as quickly back to equilibrium as it would on Earth. This means for every Earth tick of the clock on the moon will have ticked 0.408 times. Therefore, if one Earth day is passed, we take 24 hours and multiply 0.408 as the factor by which the pendulum clock slowed down, and we get a 9.78 hours on the moon pendulum time. Now what we need to do is convert that 0.78 hours to minutes, and do a quick little dimensional analysis for that, and we get 0.78 hours is 47 minutes. Multiply 0.78 by 60 minutes in 1 hour. This means that our time on our moon clock after one complete Earth day would be 9:47 a.m. This should make sense because the acceleration due to gravity on the moon is less than half the value on the Earth, so we should still be in the morning on the pendulum clock compared to the Earth. All right, that'll do it for our solutions to problems 15 through 17. More to come in class as we do problem 18 together tomorrow.